introduce the speaker, I just want to give you an update that we will have our last department seminar next week of 2019. It will be given by Dr. Walowski Ling. Her talk is going to be Azimuth PP seismic measurements, past, present, and future. Okay. So today, again, before I introduce our speaker, I just want to introduce you one of my very close collaborators, Alexander Haywader. He's working at NASA, JPL, and also at UCLA. He's a lens sniper. All right, so I'm very excited to introduce not so close collaborator, but a very good friend, Dr. Kristina Walowski. Kristina is from LA. She grew up there, and then she went to UCLA when she was for undergrad. After that, she went to University of Oregon, working on geochemistry, isotope. After PhD, she did a postdoc at University of Edinburgh for about a year or so. Year and a half. And in fact, most of what she's talking about today is related to a postdoc, right?
Yes.
Yeah, so in 2017, early 2017, she came back to the U.S., joined the faculty at Middlebury College, so that's in Vermont. So she has been an assistant professor there since. Kristina, she's a chemist, so if anything you like, just add geochemistry at the end. That's what she's interested in. Okay? So mantle geochemistry, isotope geochemistry, lunar mantle geochemistry, ocean cross alternation, ocean island basalt geochemistry. Okay, so those are things she's interested in. So basically, you can measure elements and then diffusion or how isotope evolve in time that she's interested in. And besides that, you probably know about me that I'm very interested in learning different languages. So I've been learning, I know Chinese, English, and some of German. I've actually learned my only single word, Polish, from Kristina. You will ask her what it is after her talk. So today she's going to talk about tracking volatile recycling in the heterogeneous mantle, and will be something about boron isotope. And then she told me boron is not boring, okay?
All right, thank you so much for the introduction, Menghan. It really is both a privilege and a pleasure to be with you today and to be able to share my work. As Menghan told you, was mostly collected while a postdoctoral researcher at the University of Edinburgh. So you'll notice a whole slew of UK-based collaborators, which of course this work would not be possible without. So without further ado, where I'd like to start is just why do we care about volatiles in the mantle? So this is just a sort of nice schematic diagram of the upper mantle and how plate tectonics introduces volatiles into the mantle system. But why are we interested in these cycles in the first place? So one is that the mantle is actually the largest reservoir for many volatile elements like carbon, nitrogen, and sulfur. And it turns out that the volcanic release of these species over time has played a really major role in Earth's history, and specifically the chemical cycles that have been able to sustain life and create life on this planet. The input and output of volatile elements through the process of tectonics and specifically subduction have also played a huge part in both the physical and the chemical evolution of Earth's, the solid Earth as well. So what do I mean by that exactly? So in terms of the solid Earth, we know that volatile degassing actually drives volcanic eruptions. We know that the introduction of elements like hydrogen into the mantle reduces rock solidi. So hopefully you guys remember this from introductory petrology. A pressure temperature plot, the red line being the geotherm, and the geotherm being depressed or being the mantle peridotite is able to melt at lower temperatures when you add hydrogen to it. And then of course, when you add hydrogen to mantle minerals like olivine, it can actually help facilitate mantle convection by reducing rock viscosities. So for all of these reasons, volatiles really influence geologic process. And so what my goal is to better understand both the origin and the distribution, specifically ultimately understanding the cycling of water in the mantle. And this is a pretty critical area of research in the earth sciences, which actually came up in a lot of conversations that I had with people today. So a little bit of an outline. So the first thing I'm going to do is get a little bit more into volatile cycling in the mantle and why exactly we're interested in boron isotopes. So I just talked about why we care about things like carbon and hydrogen. So where does boron come into this story? I will then go into part 2, where I'll talk a little bit about work that was published earlier this year in EPSL. And this is a really detailed comparison of boron from 2 different ocean islands specifically. And then I will go into part 3, where I'll talk about our global data set and what the global perspective of the boron isotope system in the mantle might be telling us about mantle heterogeneity and the evolution of the mantle over time. Okay, so when we think about the mantle, we usually think about kind of an interesting schematic view, perhaps an upper mantle, slabs descending into it, and then lots of different blobs. And so the reason why there are blobs in this schematic diagram is because there's been pretty extensive work with regard to trace elements and radiogenic isotopes that have identified differences in the depleted upper mantle that is sampled by mid-ocean ridge basalts, and that morbs, mid-ocean ridge basalts, look chemically different than the basalts that are erupted at ocean islands. And research suggests that because of these differences, the mantle is likely not homogeneous. So it is a heterogeneous reservoir. Specifically, the work people have done at ocean islands looking at different trace elements and radiogenic isotopes not only suggests that the mantle is heterogeneous, but that these heterogeneities are derived from primordial components or components in the mantle that have changed very little or not at all since the Earth formed. And that some of these heterogeneities, which have all these really funny names like EM1, standing for enriched mantle 1, enriched mantle 2, or HIMU, these have been introduced to the mantle over time because they have isotopic signatures that are derived from processes that occur at the surface of the Earth. So these must have been introduced over time via tectonics. And so the goal of this work is in these different mantle settings, whether they be recycled, the upper mantle, or the deep primordial mantle, what's the proportion, the distribution, and the character of the volatile elements that have been recycled over time. Okay, so there's a problem with this. It turns out that volatile elements are in fact volatile. They like to be in the gas phase at the surface of the Earth, and so when they get to the surface, they drive volcanic eruptions and are totally lost to the atmosphere. So if you were to just pick up any old piece of lava or scoria at the Earth's surface, it would essentially be devoid of water. And so one way around this is by utilizing melt inclusions. So melt inclusions are small parcels of melt that are trapped in crystals growing beneath the surface at depth. And often this can happen before significant volcanic degassing occurs. The other thing we can do, in addition to using melt inclusions, is we can utilize proxies, or elements that kind of behave like volatiles during high temperature processes, but aren't sensitive to volcanic degassing. And so in this case, we've decided to look at boron isotopes. Boron isotopes are particularly interesting and could be really great for tracking heterogeneities in the mantle because, first of all, they behave really similar to things like hydrogen and carbon during high temperature processes, but again, they don't degas from a magma during eruption. In addition, as this schematic diagram sort of illustrates, boron fractionates really strongly at the Earth's surface, but it does not get perturbed during high temperature processes in the deep mantle like during melting. And so at the surface, seawater has boron that's really heavy, so you'll notice that it's plus 39 per mil relative to mid-ocean ridge basalt, which is -7 per mil. And so if you hydrothermally alter mid-ocean ridge basalts, you get altered oceanic crust that has a positive delta B. Serpentinized peridotite, also quite positive. And so you can imagine if you're adding these seawater altered heavy boron isotope compositions to the mantle, and add them and create a heterogeneous reservoir, they will have boron isotope fingerprints that are relatively positive relative to the surrounding mantle, which is quite light. There is some continental weathering can also create light delta 11 boron signals in the crust. Another important process is also the gradual reduction of boron and delta 11B through metamorphic dehydration of subducting slabs. And I'll also point out that in addition, so we have a pretty good value for MORB, but part of the reason for this study is also to better constrain what that primitive or primordial mantle delta 11B actually is. And so a lot of this work comes from work that was originally done in arc magmas. And so when you go to arc magmas globally, you actually find that the delta 11 boron here on the y-axis relative to here, we have boron essentially normalized to niobium. So things to the left have more boron, things to the right have less boron, but here normalizing away differences in degrees of fractional crystallization. But what all this previous work found was that if you look at arc lavas globally, they're easily explained between mixtures of the depleted upper mantle, subducted sediments, as well as those serpentinites and altered oceanic crustal fluids. And so we see those delta 11 boron fingerprints of recycled materials in arc lavas. We also see evidence for that progressive dehydration. So what do I mean by that? So on the left, here's just an example of a downgoing slab. That slab is color-coded by the amount of water remaining in the downgoing slab. So what you'll notice is via subduction, slabs progressively lose their water. And during that process, boron actually gets reduced. So if we start, somewhere here, we have a nice positive delta 11 boron, so altered oceanic crust signature. And as the altered oceanic crust progressively dehydrates with depth, heavy boron is released from the slab, and so the residual slab becomes isotopically lighter. Past this point, at higher temperatures, we expect or predict no further isotope fractionation into the mantle. But this is another way we can lose boron and fractionate the isotopes. And of course, this process is going to be dependent on the amount of dehydration experienced by the thermal parameter of the slab. Okay, so thinking about boron isotopes and the complexities of volatile recycling, the hypothesis that I'll try to test today is really simple. It's just that recycled components in the mantle, so things like EM2, HIMU, or EM1, should have a different delta 11 boron composition than the primitive or primordial mantle that has not had heterogeneities introduced to it. So if we sample these different M members at ocean islands, recycled components and primitive or primordial components will have resolvable differences in their delta 11 boron compositions. So that's where we start getting into part 2, a detailed comparison of reunion, which is a primordial component, and La Palma, which is previous work has determined to be a young HIMU, so recycled, and specifically recycled oceanic crust component. This here is a really nice image of the island of La Palma. It's actually looking towards the north. These sort of snowy mountains in the background are the peaks of the old Taburiente Shield volcano. Most of the samples we looked at were actually from this younger rift zone. And actually that is the Atlantic Ocean in the background. So when you think about mantle geochemistry, hopefully a lot of you think about this classic diagram of 8786 strontium versus 206-204 lead. And what this nicely does is I like to call it the handprint diagram. And this is one way geochemists have been able to identify heterogeneities in the mantle. So EM1 having signatures of low 206-204 and elevated 8786 strontium. EM2 off in this direction, represented by places like Societies in the Azores, or the HIMU component jutting out here. So the two samples I'll be showing data from are from Reunion Island. So Pitcairn de Cunha, this is a small cone on Reunion Island, and the island of La Palma, in the Canary Islands. La Palma is a HIMU-like. It's silica undersaturated, and previous work has shown a recycled oceanic lithosphere in the source. Reunion Island's pretty different. These are tholeiitic magmas. The source is homogeneous. It's a really long-lived mantle plume, and it has fairly moderate to high helium isotope ratios. For those of you who don't know where these places are, Reunion Island is just off the eastern coast of Madagascar, where La Palma is off the northwestern coast of Africa. So from Reunion, we collected samples from Pitcairn de Cunha. This is a small cone, a parasitic cone on the currently active Pitcairn de la Fournaise volcano. From La Palma is actually the westernmost of the Canary Island chain, and also one of the youngest. Similar age to El Hierro. Most recent volcanism here was actually in the 1970s, although Volcan Duraznero actually erupted. This sample is a cone that erupted in 1949. So from this location, we have 3 samples, one from the older Taboriente Shield, and then 2 different samples from the currently active Southern Rift Zone. So what do I mean by samples? So to collect samples, when doing melt inclusion work, you want material that quenches as rapidly as possible. So we take the tephra, or the explosive portion of that eruption, so scoriaceous material and loose ash particles. We pick out individual olivine phenocrysts, and then we polish those individual phenocrysts to expose naturally glassy melt inclusions that are hosted within these minerals. From there, we take these melt inclusions, which we expose through polishing. We analyze them through 2 different secondary ion mass spectrometry methods. First, we actually measure the boron isotopes on the larger instrument, the 1270. This was done at the University of Edinburgh at their ion microprobe facility. And then we also measured water, CO2, halogens, and boron, and a suite of trace elements using the 4F at the University of Edinburgh. Okay, so a little bit about the major element compositions. So just to really highlight the differences in these 2 samples. So SiO2 versus alkalis, so classic total alkali silica diagram. Reunion Island, again, these are subalkaline tholeiitic basalts. Each one of these symbols actually represents an individual melt inclusion data point. And here showing the data from La Palma, so these are a bit more alkalic. Barranco Fagundo, so that is actually the samples from the older shield volcano, which have the most elevated lead-206-204 ratios, are a bit more basaltic and less alkalic than the southern rift zone samples, which tend to be more basanitic to tephritic in composition. Another thing we have to think about before we really get into the boron isotopes, though, is the fact that what I mentioned earlier is that subducting slabs tend to have, or can have, quite heavy boron. And part of that is because seawater has a lot of boron in it. Unfortunately, our basalts that erupt at ocean islands, that magma has to ascend through oceanic crust. Because that oceanic crust may have become altered, it's really important that we screen for potential contamination. So here we have a plot showing boron versus delta 11B. This is from Brownson et al. 2012. And what this study showed was that mid-ocean ridge basalts en route to the surface can actually increase in their boron concentration and acquire light delta 11B through adsorption, or essentially assimilating low temperature geothermal fluids. So that is in the shallow crust. You can also get elevated delta 11 boron through assimilation of altered material in the crust. And so unfortunately for the system of boron, contamination can cause both light delta 11B and heavy delta 11B. And it doesn't take a lot of boron to really alter the signals. So the samples I'll be talking about have about 1 to 4 ppm boron. And so really minor assimilation, less than 3% of anything like seawater, brines, or altered materials can alter the delta 11B by several per mil. And so each sample needs to really individually be assessed to determine the true boron signature of that mantle source. And so this is one of the reasons we decided to focus on melt inclusions for this study, as opposed to just looking at dredged seafloor glasses. And part of that, so this diagram shows water versus CO2. And what you can see, so here are individual melt inclusion data points from Reunion Island. And so what this is showing you is that all of these melt inclusions have water and CO2 that suggests that they were trapped between 1 to 2 kilobars depth. So because melt inclusions are being trapped at depth, hopefully that means is that they're seeing less of the assimilation that could happen very shallowly. So essentially, melt inclusions and the host olivine are protecting those samples from crustal contamination. Additionally, we look at relationships between K2O and halogens like chlorine to additionally screen for seawater alteration. So once we screen for seawater contamination using our melt inclusions, we can actually get some values for delta 11 boron. So here, a plot showing delta 11 boron versus nothing. So this is just showing you sort of a bunch of data, previously published data. So just to highlight a few things, mid-ocean ridge basalts were well established by recent work by Horst Marshall to be about 7.1 plus or minus 1. That's that gray bar here. But additionally, what I have is some data collected in 1995 from some old methods. But you can see that some of that data, Hawaii plots here -10, where more recent work from Hawaii got pretty different values for delta 11b. A lot of previous studies also suffered from those crustal contamination issues that I was talking about. So here, showing Iceland, this study inferred an initial value of delta 11b of -8, but that contamination created an array that went down below -14. And so also I did want to show that those arc magmas, again, having values overlapping with mid-ocean ridge basalts, but also tend to trend to more positive values. So looking at our data, so purple, that's Reunion Island, that's our primordial mantle component. That value overlaps with the mid-ocean ridge basalt field, where samples from La Palma, again, this is the HIMU sample that has previous work has identified an altered oceanic crust component in the mantle source. These melt inclusions actually have slightly lighter delta 11b with an average that goes down to about -10.5. And the other thing I want to point out, the main reason I'm putting arc basalts here is that all of these mid-ocean ridge and ocean island basalts, ours, as including previous studies, all tend to have lighter delta 11b than most arc magmas. So looking at these values in a little bit more detail, here we have delta 11b on the x-axis, boron over zirconium on the y-axis. So again, here we're ratioing boron to zirconium. This is removing any differences in degree of partial melting or fractional crystallization, which is important because these are very different types of basaltic magmas. And so again, what we're seeing, reunion samples, so the big symbols are an average of the melt inclusion suite, so each one of these is an individual melt inclusion data point. Reunion having sort of heavier boron isotope compositions than the La Palma samples here. This black symbol is again mid-ocean ridge basalts, so that has very similar delta 11b to Reunion. But here what you can also see is not only do these La Palma samples have lighter isotope values, they also have lower boron over zirconium ratios. This is telling us that not only do we have lighter isotopes, but there's less boron in the mantle source. So fractionated isotopes and actually less boron. So to better understand what these relationships are, so sorry, this is actually flipped. So here we have delta 11b on the y, boron over zirconium on the x-axis. And so what we did was we actually modeled mixing between dehydrated slab components from different papers. So 2 different papers that actually modeled how boron fractionates in subducting slabs, and how that mixed with mid-ocean ridge basalts actually really nicely explains the variation we see. And so the data from La Palma, those light isotope values, in addition to those low boron over zirconium ratios, suggest that the dehydrated slab component in the mantle source at La Palma can be explained by a slab that's very dehydrated. So what do I mean by that? It means a slab that is subducted to about 200 kilometers depth, and all the boron has been lost. It's been recycled back to the arc, and the slab no longer has boron in it when it gets recycled down into the mantle, suggesting that subduction is quite efficient at stripping boron from subducted slabs, at least to explain the source here at La Palma. What's interesting is that we actually find really similar relationships between volatile elements. So here we have delta 11B, and now I'm showing water over cerium. So the maximum water measured in a suite of melt inclusions normalized to cerium to remove any variability in fractional crystallization. So again, we look at reunion, MORB, reunion, that primordial component, mid-ocean ridge basalts, the upper mantle. We find that the La Palma samples, again, have lower water concentrations with those lighter boron isotope compositions. And again, this can be really well explained by a subducted slab source or a recycled oceanic lithosphere source that has been very dehydrated or stripped of its light elements like water. So a boron poor, potentially water poor, subducted slab in the source. Okay, so a few conclusions there. So what this data set is suggesting is that it does resolve differences in the delta 11 boron composition of recycled components and primordial components, and we can measure those. Our data also suggests that this difference is due to the presence of recycled subducted slabs or oceanic lithosphere in the HIMU mantle source. We also find that the primordial component has a boron isotope composition and concentrations that are essentially indistinguishable from the depleted upper mantle, which is actually fairly interesting because it's usually slightly more enriched, which is why this end member is considered depleted. In addition, that oceanic lithosphere seems to be very dehydrated or stripped of its light elements. Okay, so what does this look like on a global scale? Does this relationship hold true for ocean island basalts globally? So to test that, we got samples from 8 different ocean islands, most of them from the Atlantic, a few from the South Pacific. So what I'm going to do is I'm actually just going to march through the delta 11 boron compositions that we measured at each one of these ocean islands. Open symbols are glass and scoria. The filled symbols are averages of melt inclusion suites. So here we have reunion, that's that primordial component, overlapping with MORB at just around -7 to -8. Looked at Fogo in the Cape Verdes. This has been interpreted to be a mixture of EM1 and HIMU. What's interesting here, so really highlighting those issues with crustal contamination, the melt inclusion average is quite negative, and it looks like that the erupted scoria has heavier boron, which is actually the result of contamination en route to the surface. We looked at scoria from Ascension, melt inclusions and dredged glasses from Pitcairn, which is an EM1. The Ross Seamount, this is one of the McDonald's Seamounts, is an EM2. Tristan de Cunha, interpreted to be mixtures between EM1 and EM2, also having those light isotopic values. St. Helena, unfortunately, we were not able to get melt inclusions. This is sort of the classic HIMU locality. And then that data I already showed from La Palma. So there seems to be a little bit of variability, some things that are lighter, a lot of things that overlap with reunion. If I then put the MORB box there, what we'll notice is that most of our samples have uncertainty that makes them indistinguishable from MORB. We don't actually measure anything that's heavier than MORB, in a statistically significant way. There are a few things that are a little bit lighter. So thinking about this in terms of how I set up this problem and our hypothesis about the recycling of components and the variability we see in arcs, here just showing delta 11b and kernel density. So ocean island basalts from this study, mostly in that sort of -8 per mil. There's a little bit of a light shoulder. Mid-ocean ridge basalts having a very narrow range around -7 per mil. And these are very distinctly different from the huge range that scientists have measured in mafic arc magmas. So essentially very little variability in OIB, despite the fact that many of these are coming from recycled components. So very little variability when compared to mafic arc magmas. Interestingly, this little shoulder in ocean island basalts is dominantly the result of enriched mantle 2 and HIMU end members specifically. And what's really interesting here, looking at now delta 11 boron versus boron concentration, not only do ocean island basalts show very little variability in their delta 11 boron or their boron isotope compositions, but they also have very little variability in their absolute boron concentrations, especially when compared to mafic arc magmas that can have upwards of 40 ppm boron. This is particularly interesting because most ocean island basalts are very small degree melts of the mantle, so 1, 2, 3% partial melts. And so you'd expect that in those low degree partial melts, you would have enrichments of incompatible elements like boron. And what we're really not seeing enrichments at all in boron, despite enrichments in high field strength elements, as well as enrichments indicated by radiogenic isotopes. So here again showing that plot of boron over zirconium. So things that have more boron in the mantle source are going to go to the right. Things that have less boron in the mantle source are going to go to the left. Versus delta 11b. Every single one of these data points is a melt inclusion. So reunion, that primordial component overlapping with an average of mid-ocean ridge basalts. La Palma in pink. So then if we look at the ones I just added, so EM2, EM1 HIMU mixture, as well as EM1, we're finding that for all of these enriched mantle components that are interpreted to be recycled into the mantle over time, all of these have less boron than the depleted upper mantle. And they have a very restricted range in their delta 11b, most of them actually showing lighter boron than the depleted upper mantle, with EM1 having essentially an indistinguishable delta 11b, but lower boron concentrations. And I said all those things. Okay, so distinctly lighter delta 11b for the EM2 and HIMU end members. Again, looking at water in this, so I will note that we have not corrected the water for things like diffusive hydrogen loss, so these are minimum estimates for water, but still looking at the maximum water, measured from each melt inclusion suite. Again, we see, just like boron, it seems that there are lower water concentrations in all of these recycled heterogeneities relative to both mid-ocean ridge basalts and reunion, which represents that primordial mantle component. So recycled materials seemingly having less water, less boron, and similar or lighter boron isotope values. So what does this really all mean? So as I sort of showed you with those mixing models before, when we look at the combined data set of boron isotopes, boron, and water, it suggests that processes in the upper mantle during subduction, dehydration, and at arcs very efficiently strips boron and potentially water from slabs, which are then recycled into the continental crust, and that subducted slabs are bringing little in the way of boron into the deep mantle over time. So our data suggests that these heterogeneities are not preserving enrichments in volatiles, and actually the opposite. They're preserving depletions in light elements. But there's still a lot of outstanding questions actually in this work. So there's a lot of unknowns about the behavior of boron during mantle melting, specifically in the presence of garnet. So a lot of work needs to be done from the experimental side, thinking about how boron partitions during mantle melting. We also like to think about the data set more broadly and how it correlates with different mantle anomalies that have been identified previously, like the Dupal anomaly. And we're also really interested to see what a comparison with other light elements, so potentially halogens like chlorine and fluorine, which should behave like boron, tell us about the nature of mantle volatiles and that efficiency of volatile recycling in arcs. But I think a big takeaway of this study is that boron isotopes are absolutely decoupled from a lot of traditional radiogenic isotope systems. They're also decoupled from noble gas isotope systems and seem to provide a really unique perspective on the volatile character of mantle source heterogeneity. And with that, I'd be happy to take any questions.
Questions? Yes, James. Hi. So in your talk, you interchangeably used the term primordial mantle and phoso, but in your cartoon earlier, you distinguished between those two reservoirs. So I guess,
sorry, that was something I needed to fix in the phoso. I didn't catch all the phosos, but there's been recent work at Reunion looking at neodymium isotopes that suggests that there is a primordial component in that source. And so that's why I've used primordial at Reunion specifically, where I think in terms of its strontium and its lead and things like that, it's sort of more focal zone, but it has a pretty, it doesn't have that high of an RA, so it's like, so its helium-3-4 ratio is only like 12 or 13, it's not 20. But the neodymium isotopes provide evidence. So.
And were you comparing the same samples, like so the same sample that had 15 RA, did you measure that?
We did not measure that in the same samples. But I would also say that there's unpublished data from like Baffin Island, which also has very similar delta 11 boron. So it seems that the primordial component at different, if you go to different ocean islands that have high helium-3-4 ratios, they do not have boron isotope values that are different from MORB.
Early on you said that boron behaves like a volatile.
In that it behaves incompatibly, generally.
Okay, I think you answered my question. I was going to ask you simply why.
It's just, yeah.
At the beginning you said that you might talk about the origin of volatiles and the origin of boron in terms of the potential building blocks that could have brought boron into the planetary system. Can you give us any thoughts on that?
Yeah, so I think, I don't think so. So I think what this data set helps resolve is that whatever the Earth started with, it seems to be what DMM or the depleted upper mantle still is. Or there isn't a big difference there. Or that we're able to put better constraints on what primordial boron or the primordial boron fingerprint may be.
Is there a lot of boron work in meteorites?
I'm not familiar with meteorites. There's been a little bit of work done on the moon, but it's not, there hasn't been much work done. The bulk method is difficult. And then doing in situ, you need glasses, which I think are very difficult to get in things like meteorite and lunar materials. But my understanding of a lot of lunar materials, it's actually really in the same range of MORB and OIB, the little work that's been done.
I guess I'm wondering if you sort of introduced this as like a tracer for volatile cycling, but we can see recycled volatiles in other systems, like we've seen recycled components of noble gases. Why doesn't boron get recycled during subduction? Does boron completely leave the slab? Is that the idea?
That's what I was trying to explain, is that it seems like boron is getting recycled back to the arc. So it's staying in the upper mantle and getting recycled through the arc system. It's not staying in the slab and going down into the deeper mantle. So that's why those heterogeneous, so they have less boron than MORB. And so if they were enriched slabs, if they weren't getting stripped, you would expect them to have the same or higher boron concentrations than MORB.
I think you mentioned when we talked earlier that boron doesn't degas during.
It does not. No.
Rich? So I have a hard time following what the mass balance of boron is in the silicate earth. So you've got an element that doesn't get subducted back down into the deep mantle. What's the percentage of boron sitting in the crust with us of the overall silicate earth? What is the concentration, or what's the proportion in the convecting upper mantle? Do you have rough numbers for this, like particularly what's in the crust?
In terms of
50% of all
boron? Oh, I don't think we know that. So this is, I mean, I guess that's something that I can start thinking about with this data set. If you sort of make an assumption of, if you assume that boron partitions in the exact same way as zirconium, so people just haven't done partitioning experiments with boron at those of pressures and temperatures of the deeper mantle. You can infer those based on how boron behaves. So it behaves, at least in mid-ocean ridges, like things like zirconium or phosphorus.
So do you know off the top
But
of
I
your head
haven't done the mass balance.
average boron concentration in the continental crust? What's that?
I do not know off the top of my head of average. And I actually, that's a good question. There's, yes.
We're going to look it up and run Go or something.
Yeah, what boron is.
Yes, if I understand you correctly, right? So the upper mantle represents by MORB, and the really deep part of the mantle, for the boron concentrations and isotopes, they're similar. Is that right? That's
Yeah.
what you see.
Yeah.
In the middle, lower mantle, but above the deep mantle, is actually devoid of boron. So what if they don't recycle to there, right? Because boron just gets stripped. How do you, at the beginning, remove that boron? Do you see what I mean? Right, because your primordial ones has a certain amount of boron, but right now they don't have that anymore, so they lost it.
I'm not sure I'm following the question.
So I would think that at the beginning everything would be the same. Then process started, so you lose boron.
So, and that's what I was showing. So like, those heterogeneities have less boron in them.
How do you create that?
Through subduction.
Mm-hmm.
Subduction is stripping those elements from slabs. Oh, I guess, are you just...
No, I'm saying that, say the primordial, right? And
Yep.
now the one that's, the layer that's above the primordial.
Mhm.
At the beginning, they may still have boron. Now they don't. Right now you see them, they don't. But if you think about it, they are made of the primordial materials at the early Earth stage. Somewhere they have to lose that boron.
Oh, the boron is being concentrated in the crust. That's why the mantle is losing boron.
Then why is the primordial has such a high one?
That's just what it
The
started with,
big
and then
one.
over time it's becoming, there's less boron over time.
And you have
I guess is someone I don't,
I'm just saying that, I just want to know what's the mechanism causes the top and the bottom is the same. In the middle, they are less. Some process has to make that differentiation, right?
so you're saying why is more the same as primordial?
Yes.
That is a good question. I don't know if I have I don't have a good answer for that.
Because I'm thinking it's either top heavy, right? It's differentiated through the depth, or it's always have that differentiation. Now, it's somehow you create this boundary layer.
But I don't think
On
so.
top
I
and
think
the bottom.
one uncertainty in what you're saying is just that we see heterogeneities in the mantle that are sampled by ocean island basalts. I don't think we know exactly where those are. Like, are they in the middle of the mantle? Are they enrichments in the upper mantle that are partially melted by thermal anomalies? Are they coming from the core mantle boundary? I don't know if we know that for any of these ocean island end members. For certain, anyway.
Is there a way to look that from geophysics data, seismic data?
Perhaps that's a good question for Nick. Is Nick here? I think it's all about the size and whether or not you can resolve
Big
it.
enough to be imaged.
Yeah, so there's groups that suggest that the large low velocity provinces in the deeper mantle are the source from some of these heterogeneities. So they could be sort of these slab graveyard materials. So piles in the lower mantle. So.
Oh yeah, James.
Yeah, I have tons of questions, but this is the most recent one in my brain. What's the process that's keeping, well, I don't know how to say it. You're losing boron during dehydration.
Yeah.
You're keeping some of it in the slab. Why isn't all of it just leave? Like, why aren't you just losing all of your boron?
All of it.
Like, what's holding it back? So it's held in some minerals, right?
It's held in some minerals. I guess
Right.
it's sort of like, you think about partitioning, right? So almost all of it's going to go in the melt, but unless the partition coefficient is like, there's always going to be some of it that remains in the mineral, right? It's very, very little. I think if something like less than 0.01 ppm total in the source is what is what you can infer. If you sort of like back calculate, you assume that there's like a 3% partial melt of the mantle, and that 3% partial melt has 1 weight% water. You infer what the source had, and it's like 0.01 or like less than a ppm in the source. So it's very, very, very little.
And I guess my follow-up question then is there any other dehydration proxy that you can plot your boron concentration or delta B is what you use against? So I don't know, like I guess for sulfur you could plot like sulfur versus lead because you lose lead during subduction. And you can look at sulfur versus lead in that process, but I don't know about boron. Where is
Yeah, so it looks like the lighter, actually I didn't show this plot, but there is a general correlation with lead 206, 204. So things that have higher 206, 204 have lighter delta 11B.
So then you could probably plot boron versus sulfur.
Probably.
Because the lead is held in sulfur.
Probably. Yeah, I actually have, that's actually the next diagram. So just keeping in mind that it's not the same sample, but yeah, so here 206, 204 lead. St. Helena, that has problems with contamination. But if you look at just the melt inclusion data, there's sort of a loose correlation where the lightest delta 11B samples are correlated with the highest 206, 204 lead. And then sort of delta 11B versus R over RA, you see the same correlations that you see with like water or boron over zirconium as well.
All right. I think we can thank our speakers, Kristina again, and then we